In this video, we are going to look at solving exponential equations using logs. And I have the title Alternative Method because there's a second video in here that shows about solving exponentials using logs. But it involves using a method that is used a lot in calculus and other higher level maths. But I wanted to start with a way that's a little bit easier for you guys and more familiar with some of the things that we've been doing when we've been converting logs and exponentials back and forth between the two. So let's start out with a problem that you probably could be able to do, solving using a method you already know, common bases. So let's say we had 4 to the x equals 64. Well, when we looked at solving using common bases, we said, okay, well, we have a base of 4, and so let's see if we can write 64 as 4 to the power of something. So in this case, we could say, okay, 64 is 4 cubed. So we really have the equation 4 to the x equals 4 cubed. So now you can go back to solving using common bases, and you can say, well, x equals 3. Well, this is one way to solve this problem, and this is an excellent way to solve it, but we can solve it using logs as well. So again, let's start out with 4x equals 64. Now, before you try to convert anything with a common base, let's go ahead and change it into the log form of the equation. We're going to convert 4 to the x equals 64 into a logarithm. So this means the log base 4 of 64 equals x. Now, in this case, we can actually evaluate this because we know that this is the power that makes 4 into 64. And the power that makes 4 into 64 is 3. So we can say that x equals 3, or 3 equals x, by the symmetric property. So we just solved this equation using logs. In some ways, this is easier for some people. Common basis is good too, but we need to know how to use the log method because sometimes we can't write both sides of the equation with a common base. So here we have 7 to the power of x equals 9. Now, I don't know about you guys, but I don't know a way that I can write the number 9 as 7 to a power, at least a nice integer power that I already know. So instead, let's go to the log method. Let's think. Let's rewrite this as a log equation. We know that the base is 7, the exponent is x, and the resultant is 9. So when we write it as a log, we would say the log base 7 of the result, which makes it the argument of 9, equals x. So now we know that x equals the log base 7 of 9. And again, this is the power that makes 7 into 9. And I don't know what that power is, and it's actually a decimal. So at this point, we are done. Sometimes you want to get a decimal approximation, and that's easy enough to do. In your calculator, now that we have these advanced calculators that can do all of the bases, we would just type in log base 7 of 9, and we would get its decimal equivalent. Usually, we want to leave it in the log form because that is the exact answer. Whenever we try to find that decimal approximation, generally it's a decimal that goes forever, and so it's not the exact answer. So it's just an approximation. Again, this is the exact answer, leaving it in log form. So now this one's a little bit trickier. We have 2 to the power of 3x, and it equals 30. Again, since my exponential is already isolated, and I know I can't write 30 as 2 to the power of something, I'm going to go ahead and convert it to logs. So I have the log base 2 of 30 equals 3x. Now, unlike the last example, we don't have x by itself, so we really haven't finished solving this. Before we can say we're done, we have to isolate x. So again, you're going to just use your basic algebra skills. We're going to divide both sides by 3. So we have 1/3 of the log base 2 of 30 equals x. Now that x is isolated, we're done. We have this problem solved. And since I want the exact answer, I'm going to leave it in this form. Again, you could use your calculator and type this result in, and that will give you the decimal approximation of the answer of what is 1/3 times the log base 2 of 30. 10 to the power of 5 minus x equals 8. Now if we want to solve for x, we need to get x out of the exponent, so we're going to convert. Since the exponential is already isolated, I can convert right away. I'm going to say that this is the log base 10 of 8 equals 5 minus x. Before I go into isolating x, I am going to just rewrite this using the common base, which means we don't actually need to write that little 10. So we can say that the log of 8 equals 5 minus x. Now let's just focus on the algebra. The log of 8 is just a number, so you can treat it like a number when you're solving. I know that I need to get 5 by itself, so I'm going to subtract 5 from both sides. So the log base 8, or the log of 8, minus 5 equals negative x. Now, I can't put those two things together. The log of 8 and 5 are two different things. I can't combine it into saying like the log of 3 or something. They're two separate parts. So when I actually find that decimal approximation, I'm going to have to keep them separate. So that's why I'm keeping it separate here. There's one last thing we need to do to isolate x, and we need to get rid of that negative. Remember, that's negative 1 times x, so I'm going to divide both sides by negative 1. So we end up with just x by itself on one side. We have the log of 8 divided by negative 1, which is negative log of 8. And then we have minus 5 divided by negative 1, which is now a positive 5. So when we leave this in its exact form, we can say that x equals negative log of 8 plus 5. And again, your calculator will give you a decimal approximation if you type that in. Type in the whole thing, negative log of 8 plus 5, and that will get you what the decimal approximation of x is going to be. So just like when we solved exponentials using common bases, our very first step was always to isolate the exponential. And in this case, the exponential is e to the x plus 1. So it's very, very much not isolated right now. So let's go ahead and do that. To do that, the first thing I want to get rid of is that 2. So I'm going to subtract 2 from both sides. Now we have negative e to the x plus 1 equals negative 19. We're almost ready to convert, except for the fact that I see that negative there. We need to get rid of that. And we know that this is negative 1 times e to the x plus 1. So I'm going to divide both sides by negative 1. So what we end up with is e to the x plus 1 equals 19. Now the exponential is truly isolated, so we're ready to convert to logs. So in this case, it is going to be the log base e of 19 equals x plus 1. But we know that the log base e is just the natural log, so when we rewrite this, I'm going to say it's the natural log of 19 equals x plus 1. We finally finish up by getting x by itself. So we can say that x equals the natural log of 19 minus 1. And this is the exact answer again. We can find the decimal approximation by using our calculator and finding the ln, natural log of 19, and then subtracting 1. Now this one looks a little bit trickier, but again, you want to think about those steps that we used when solving with common bases, because the first part of those steps remains the same, even when there isn't a common base. Those steps involve getting the exponential by itself. So in this case, we have to divide by 3 first. That will cancel each other out, and we're left with 2 to the x plus 4 equals 15. Now that the exponential is isolated, we can go ahead and convert to log form. So we are going to have the log base 2 of 15 equals x plus 4. Since the log base 2 isn't one of those special 2, we have to leave it just like this. We can subtract 4 from both sides, and we will end up with x equals the log base 2 of 15 minus 4. This one looks really crazy complex, but we can do it. I have faith in you guys. We're going to use our algebra skills to get that exponential by itself. I'm going to subtract 1 from both sides. So we end up with 45 equals 5 times 3 to the x minus 4. Alright, we're almost ready to convert, but first we have to divide. We have to get rid of that times 5. So we're going to divide both sides by 5. We are going to end up with 9 equals 3 to the x minus 4. So since we're focusing on converting to log form in these problems, I'm going to convert it to logs. So I know that the log base 3 of 9 equals x minus 4. So I'm going to use my algebra. We're going to get that x by itself. So we're going to say that the log base 3 of 9 plus 4 equals x. Now, this is a case that I don't even need my calculator to find an approximation for. This exact answer is a nice, pretty integer. Think about it. The power that makes 3 into 9. Well, I know what that is. That's 2. So 2 plus 4 equals x. And we can safely say that x equals 6. So in this case, we actually did not need to use logs to solve this problem. If we would have stopped and we would have looked at here, this step, we can see that we have 9 equals 3 to the x minus 4, which is the same as saying that 3 squared equals 3 to the x minus 4. So 2 equals x minus 4. And we can say that adding 4 to both sides, x equals 6. Now, you can't always go ahead and go back to your common base method, but it's important to know that one because sometimes you can. And you always want to use the most efficient method. Is one method better than the other? Well, the log method always works, even if the bases can't be the same. But when you have common bases, you might as well use them since you know how to do that skill. Before I get into the other weird method, the one I used in the other video, the calculus method as I call it, we're going to do one last one with e, so we can look at that natural logarithm. I'm going to start out by isolating, so I'm going to subtract 1. So I end up with 13 equals e to the 2x. Now when we convert it to log form, remember we're going to want to use the natural log. So we know that the log base e of 13 equals 2x. And again, we know that that really means the natural log of 13 equals 2x. Divide both sides by 2 to get x by itself. You are going to end up with 1/2 times the natural log of 13 equals x. So again, you could type into your calculator and you could get the decimal approximation of this. Or if you wanted to leave it in exact form, you would say that x equals 1/2 times the natural log of 13. So I think we're pretty good with the converting. So now I want to get into what I call the calculus method. This is one that you use a lot when you're dealing with higher level maths, and sometimes we need it when we end up with variables in the exponents on both sides of the equation. What this method involves is something called taking the log of both sides. When we solve square root problems, or when we solve squared problems using square roots, we can take the square root of both sides. So taking the log of both sides is similar. One thing to think about though is that you can take any log of both sides if you want. You can take the log base 7 of both sides. You can take the natural log of both sides. you can take the log base 10 of both sides. Doesn't matter as long as you're consistent. When you're in calculus, a lot of the times you'll see examples where you take the natural log of both sides. I know that when I was in high school and we didn't have fancy calculators that did different bases, we always took the log base 10 of both sides. So I'm going to show you a couple of different ways to do all of these problems, and you can decide which you like the best. So if we are going to take the log of both sides, I'm going to start out with the common log. I'm going to take the common log of both sides of this. It will look like this. The log of 7 to the x equals the log of 9. And again, this is the base 10, and I just don't have to write it because it's the common log. Now, according to properties of logarithms, I know that x can move out in front and become a coefficient. So I could say that this is the same as x times the log of 7 equals the log of 9. Now, remember that the log of 7 is just a number. Same with the log of 9. So if I want to isolate x, which I have to since I'm solving, I can divide both sides by the log of 7. So then I end up with x by itself, because these cancel, equals the log of 9 over the log of 7. And if we use our change of base formula, we know that this is really the same as the log base 7 of 9. And we can leave our answer like that. So this is exactly the same as the answer we got when we did this problem earlier by just straight up converting. And yes, converting is faster, but I'm working our way up to a complex example where we have to use this method of taking the log of both sides. Now I could do it again with natural logs, and you would see that taking the natural log of both sides gets you the same answer. But what I want to do in this case is take the log base 7 of both sides, just so you can see what that looks like. So let's sort of start our problem again in the corner here. It's not going to take very much space. 7 to the x equals 9. And if I want to take the log base 7 of both sides, it would look like this. Log base 7 of 7 to the x equals the log base 7 of 9. Since I did the same operation on both sides, we still have an equal equation, and we can go ahead and continue using our properties, etc. So the first thing I'm going to do is that power property. It says that I can change this to the log base 7 of 7 times x equals the log base 7 of 9. Now, before we start dividing or anything like this, let's use our smarts. Let's go, okay, this is the log base 7 of 7. That means the power that makes 7 into 7. And that's just 1. So I know that this is x times 1 equals the log base 7 of 9, or x equals the log base 7 of 9. Magic. They're the same. And they're the same as we got when we converted using logs earlier on like the second slide of this video. So again, you can see all of these methods are good methods. All of these methods are work, but it just depends on the situation that you have, which one you want to use. I know that your mind is probably completely boggled from that last example, so we're going to start afresh with a new one and focus on using this idea of taking the log of both sides. Before you can do that, just like any other exponential problem though, you need to make sure that you have the exponential isolated. So I'm going to start out using some algebra. We're going to get negative e to the x plus 1 equals negative 19. And then we're going to be good and remember that that's negative 1 times that. So we need to divide both sides by negative 1. So we will end up with e to the x plus 1 equals 19. Now, instead of converting like I did on this problem earlier, I'm going to practice using my calculus method and take the log of both sides. Since the base is e, I am going to take the natural log of both sides. So that looks like this. The natural log of e to the x plus 1 equals the natural log of 19. Because I use that same operation on both sides, I know that it's still equivalent. As long as you're consistent, we're good. That's kind of nice about algebra. Consistency is key. Now I'm going to use my property that says that if I have this exponent up here, it can become a coefficient. This one's trickier though because x plus 1 needs to stay together. That's all in the exponent. So x plus 1 times the natural log of e equals the natural log of 19. Now I know that the natural log of e is 1. So really, I just have x plus 1 equals the natural log of 19. I can subtract 1 from both sides and end up with x equals the natural log of 19 minus 1, which, if you were to go back a little bit in this video, you'd see is the exact same thing we got when we solved this problem by converting to log form. So by now I'm sure you're thinking, why on earth would you bother showing me this calculus method if I can solve all of those the same way by just converting? Well, here's an example where we can't convert. And so here's where we have to use the method of taking the log of both sides. Now you can see we can't convert because there's a y in both exponents. So if we were to convert, we really wouldn't be in a better place. So in this case, we do need to take the log of both sides. Now remember, you have a lot of options. You could take the log, the common log of both sides. You could take the natural log of both sides. You could take the log base 2 of both sides, since you have a base of 2. You could take the log base 3 of both sides, since you also have a base of 3. Really, you could take the log of any base of both sides. But I like to use the log base 10. That's what a lot of calculators know how to use, and that's kind of one of the more familiar methods, one of the more familiar things that people do. So let's go ahead and let's do that. We're ready because our exponentials are isolated. So I'm going to take the log of both sides. Oops, it's not that anymore. It's 4y plus 1 equals the log of 3 to the y. Now let's apply our power property so that we can really say that this is 4y plus 1 times the log of 2, and that equals y times the log of 3. Now I want you to remember one thing before we get too into the craziness of this problem. The log of 2 and the log of 3 are just numbers, so you can treat them like numbers. You can add them, you can subtract them, you can multiply them, and you can divide them. So in this case, I know that I can distribute the log of 2, and I can get that y out of the parentheses, which is what I ideally want to do in order to isolate y. So now I have 4y times the log of 2 plus 1 times the log of 2, which is just the log of 2, equals y times the log of 3. Now if our goal is to get y by itself, that means we want to get the y's on the same side of the equation. Right now, if I draw my line, I see that I have y's on both sides. So just like when we're solving a normal equation, we need to move them to the other side, so we might need to subtract or add. It doesn't really matter which side you move it to, but since I only have a y term over here, and I also have a number term on the left, I'm going to move my y's to the right-hand side. To do that, I'm going to subtract 4y log of 2 from both sides. So now I end up with the log of 2 equals y times the log of 3 minus 4y times the log of 2. Now again, I'm going, I can't really put these two things together because the log of 3 and the log of 2 can't be combined. So let's go ahead and we are going to factor. I know you guys are excited. We're going to factor the y out of the right-hand side. So we're going to end up with the log of 2 equals y times the log of 3 minus 4 times the log of 2. Now I'm almost done actually because I only have one y, and I can isolate that using my algebraic properties. I want you to remember that the log of 3 and the log of 2 are just numbers. So the log of 3 minus 4 times the log of 2 is something that I can do. That's a number. So it's just y times a number. I can use the property rules to simplify this a little bit, but I'm just going to leave it big for now. So we're going to divide both sides by that number. That 3 should be big. So now we have y by itself, and we can go ahead and safely say that y equals the log of 2 divided by the log of 3 minus 4 times the log of 2. We can actually use properties to simplify that statement a little bit further, but in general, if you're doing a problem like this, you're going to want to know the decimal approximation as well. So usually this would be an example that would come up in an application. So we could use our calculator to find that final result for y. We could just type in all of that, and our calculator knows what those decimal approximations are, and we can get a good idea of what y is in terms of a decimal. So here you can see, I know it was a lot, but in this case we actually had to take the log of both sides. There was no other good way to do it. In general, you're not going to ever have to use this crazy of a method. Generally, we're going to have more problems like the ones that earlier occurred in this video. So let's go ahead and recap what was just done in this video. We can go back to the very beginning and back to even solving with common bases. The very first step, no matter what, is you need to isolate the exponential. So when we only have one base that we need to worry about, one base with the exponent in it, we can convert to log form. And that involves using just going, okay, the log base b of the argument equals the exponent. Then you just need to use your algebra skills and you need to isolate the variable. Sometimes you have to use properties to do that, and that's why we learned about properties before we learned about solving. If you have the case, like the calculus case, the very last question we had, where there were multiple bases with exponents that had variables, then you have to take the log of both sides. And you can take the log of any base you want as long as you're consistent. Then, if you're using that method, you go back to isolating the variable, and again, properties might be needed in order to do this. More than anything else, you will use these first 3 steps. Only in special cases are you going to need to move into the ones where you take the log of both sides. When you do IXL sets, a lot of what they're going to tell you to do is take the log of both sides, because in general, that is a skill that always works, whereas converting only sometimes works.